welcome to lecture number 33, and in our last class I told you about how to handle AC circuits just like DC circuit analysis and how mesh analysis can be carried out. Similarly, nodal analysis, let me just write down the equations, no question of further deriving it. Suppose you have a circuit like this. I am now drawing impedances as boxes. Suppose Z1 bar, here is one voltage source, there is another impedance here and there is another voltage source here. Okay, AC, and there is Z3, Z1, Z2, this is Z3. They could be RL or pure R or pure or a combination of R and capacitance and so on. And there is another source here, say minus and plus. And here is a source and here is another resistance here, say Z0, and this is the circuit, and there may be another branch here like another impedance Z4 and another source plus minus like this. Let these sources be called E1, E2, E3, and let me put another impedance here Z5, and this is say E5. Okay, this is how the circuit is given. This is say E6. So, all the impedances I will be knowing their values, source voltages are also known, I want to calculate the currents. Now, similarly here one can apply the mesh analysis, number of meshes are 3, I1, I2, I3 that I have described. Now, I will tell you how to apply, write down the nodal equations, node voltages how to find out. So, first of all you mark the nodes 1, 2, 3 and 4. There are 4 nodes, one of them you call it O, reference node, and other 3 are A, B and C. Our target will be to know the value of VAO, VBO and VCO. So, writing down the equations of so KCL at node A, KCL at node A will be the coefficient of VAO. It will be sum of the reciprocal of all the impedances connected to 1 by Z0 plus 1 by Z1 plus 1 by Z4. This will be VA0. All will be phasors here. Similarly, coefficient of VB0 will be common impedance between A and B, that is Z1 minus 1 over Z1 into VB0, and coefficient of VC will be the impedance in this branch. So, that is Z4. So, minus 1 over Z4 into VC0, and this will be equal to the dimensionally the right hand side should be currents and source should be involved. So, E1 is a source connected to A. So, it will be E1 by Z0, E1 by Z0. So, it will be E1 by Z0 plus sign, because polarity is such it drives current towards node A. Similarly, E6 by Z4, that is also plus E6 by Z4, and E2 also is connected to node A. So, polarity is such it should be E2 by Z1. This will be equation 1. At node B, KCL similarly will be coefficient of VV0 will be sum of reciprocal of all the impedances connected to B, that is Z1, Z2 and Z3 into VV0, and coefficient of VA0 will be common impedance connected between A and B preceded by a negative sign plus, and coefficient of VC0 will be minus 1 by Z3 into VC0, and this will be equal to all the sources. So, E3 connected to B, E3 by Z2 will be current in this direction. So, that will be positive. All are complex number, E3 by Z2 plus to B plus sign. Then this is minus, this is plus. Then E5 is not connected. So, only this source and this source E2 is connected, but E2 you see minus is connected to B. So, it will be minus E2 by Z1, that is all. To B only these two sources are involved. So, this is how second equation looks like, and the third equation is at C, at node C. At node C, it will be coefficient of C will be 1 by Z3 plus 1 by Z5 plus 1 by Z4. So, it will be 1 by Z3 plus 1 by Z5 plus 1 by Z4 into VC0, and coefficient of VA0, yes, there is a connection between A and C. So, minus 1 by Z4 into VA0, Z4 is the impedance here. Similarly, coefficient of VV0 will be simply minus 1 over Z3 into VV0 and plus this term, and this should be equal to currents here, source. So, E5 by Z5, but negative is connected to minus C. So, it will be equal to minus E5 divided by Z5 bar. There is a source also connected here E6 to C. So, minus this is also minus E6 by Z4, that is all. So, these three equations just like your DC circuit analysis, except that all the numbers will be complex in nature. Then you calculate by any method you like, use your calculators, but coefficients will be complex. But the fear that we had got, if it is RL circuit, there is complex circuit like this, several sources are present. So, you have to write down the differential equation to solve for currents, that is not necessary. If you are only interested in the steady state currents, you go to the complex domain, solve it, these are algebraic equations, no differential equations, calculate it, you will be able to calculate also the powers at various branches and so on. So, all the things that we have applied in DC circuit can be applied there also. Similarly, there may be a current source, time varying current source. In case of DC circuit, what do I see? If there is a current source having an internal resistance R only, then if there is a load resistance connected here, then this circuit is equal to this circuit. You can always go to R and here is your AB. We have seen that in DC circuit and here is your R. Or if you have a battery in series with some resistance R, if a load is connected, if you have a battery and here is your loaded resistance, this is nothing but equal to, can be thought of as a current source E by R and in parallel with R, and these are the load terminals where R is there. This we are doing in case of DC circuit and all things we did earlier. Here I am telling, if you have a current source which is sinusoidal in nature, so it can be represented as a phasor, and if there is an impedance here, and here you connect some load impedance, then this will be simply equal to an impedance in series, that is Z bar, and here you can think it is a voltage source, that is I bar into Z bar, open circuit voltage, and then you have the load impedance Z L. A, B, this is also A and B. And conversely, if you have a, so a current source in parallel with an impedance can be considered to be a voltage source in series with this impedance, and then your load across AB. Similarly, if you have a source, AC source will have as its internal resistance as an ideal AC source E bar, and AB is your load terminal, and here you connect a load impedance ZL. Then this can be thought of as a current source whose value will be E bar by Z bar in parallel with an impedance Z bar, and then your A and B, and this is the load impedance. So, if it is AC circuit and I am only interested in steady state currents, powers, etc., then phasor notations can be used and can be used with ease. Only thing, complexity burden increases a bit, but nothing like solving differential equations will come in the way. It is all linear equations. So, please remember these things, this is how you will be going, and you have solved several circuits with complex impedances. Now, I will today in this lecture will now summarizing all the lectures that we have done so far. You are now in a position, if it is not a sinusoidal thing, okay, differential equation is to be written, you cannot avoid that, and voltage source can be anything. And I told you how to solve such circuit earlier, say V t, any voltage source, RL circuit, RL circuit. So, coming back to general circuit approach, okay, supply voltage could be anything, need not be sinusoidal, V t, and we found out the currents. Of course, to find out these currents, you have to write down differential equations or do something. If V t happens to be sinusoidal or DC, then there is some relief in getting the forced response quickly, those we have discussed. For example, the current in the circuit we have calculated so many times is E by R into 1 minus e to the power minus R by L into T. If V t is equal to a battery constant voltage, we have seen this with, of course, initial with the assumption that I 0 minus was equal to 0. Achha, now, today what I will tell you that this circuit, the solution of this circuit could be thought of like this, a switch, this is how we were drawing this circuit, E, and I told you I close this circuit at t equal to 0. Okay. But what I am now telling you is that this circuit, this voltage can be described using some unit step function, and you can this is same as telling that I have applied a voltage, what is called unit step voltage E into u t, and draw the circuit like this. We will define what is unit step function. A unit step function is drawn like this. It is 0 for t less than 0, I am closing the switch, and then for t greater than 0, it is E. It is not unit step, it has got an amplitude, but the magnitude is constant, whereas unit step will be like this. This is u t, and this is obviously this function is E into u t, where E is a constant number. This is t equal to 0. So, if I say there is a circuit where this voltage V t is E into u t, I mean that this voltage has been applied to the circuit. For t less than 0, the applied voltage was 0. So, this circuit will look like for t less than 0, this circuit will look like R L. This you please follow me very carefully. For t less than 0, applied voltage is 0, because E into u t. So, this I will show like a short circuit. There was no voltage existing. One may think that okay, it is open circuit, why do not you show? But my input voltage is 0. To indicate that, I say, although I have not discussed, you must understand that in an RL circuit, there the inductance is present. Therefore, some flux somewhere may link it and produce some current in this circuit, but my applied voltage is 0, that is the more important point. If you show it as open circuit, then that voltage will come here. So, input voltage I will define between these 2 points, which is 0 means shorted, and for t greater than 0, the circuit will look like R L, and here as if a constant voltage plus minus E. This is the situation. So, this is how if some function is written. So, for t less than 0, voltage applied is 0, from minus infinity to 0 it was 0, like that. Even inductor had some current that must have dissipated in R, energy storage initially long back. So, initial current will be also given and you can solve the current, but expression of the current for t greater than 0, you will get the same equation R I plus L d I dt is equal to, you write u t. I am interested to get the solution for t greater than 0. Therefore, E into u t is nothing but E itself for t greater than 0. Got the point. Therefore, this is how one of the important function called unit step function emulates the situation where you want to connect a battery across R and L. This function is one of the very popular functions. At t equal to 0, I am not sure what is the magnitude of this unit step function. So, this is unit step function. It is not defined at t equal to 0. T 0 minus, it was 0, sure. T 0 plus, it is E, and it will be E for any time to come. That is the thing of a unit step function. Now, in my previous lectures, quite earlier to the discussion we are having about AC circuit, I told you while writing down the differential equation, right hand side is the voltage, that is R I. Always bring one circuit in your mind to understand the thing. This was my V T, suppose R L circuit, R L, this is your V T. It could be any function of time now, need not be sinusoidal. That is why I am in time domain, I cannot go to phasor domain. Okay, if this is the thing, I have to find out this current I, R, L. So, I will write down the differential equation and solve it, and I will demand some initial currents must be provided to me, I 0 minus etcetera, and switching I will do at t equal to 0. This is how we have been telling to you, and then at that time I told this right hand side I put a restriction so far, and told that this is the excitation or input voltage, excitation or input voltage, and so far whatever I have done, solve these differential equations with the assumption that V T exclude impulse for V T. V T is not an impulse, is not an impulse voltage. and if Vt is not impulse voltage, we established I 0 minus is equal to I 0 plus. You recall, for an inductive circuit, what should have been the current in the inductor at t equal to 0 minus, at t equal to 0 you did something. So, I 0 plus will be equal to I 0 minus, that is what we have been telling so far. Now, I will not exclude this impulse function. So, what happens? What happens? If an impulse, if an voltage impulse is applied to an RL circuit, to an RL circuit, this impulse voltage usually denoted by delta t, as we have denoted unit step voltage as ut. This is the impulse voltage, mathematically denoted by this. Then the question comes, what is an impulse voltage? I must know, like unit step voltage was defined like this, 0 for t, any t less than 0, then it steps up to a high voltage V. This is your time axis. Now, what is an impulse voltage? That is very interesting. You see, suppose you have a voltage waveform like this, a rectangular voltage waveform. Like this, suppose, and this interval, are you getting this voltage waveform? It means that for V less than this time it was 0, for V greater than this time it was 0, but for V between this point and this point there was some step voltage sort of thing, a rectangular pulse voltage. So, this is a rectangular pulse voltage, V t is supposed like this. Then the question is this one. Suppose I say this is h by 2, or I will use a, okay, this is h by 2 and this is plus h by 2. So, what is the width of the rectangle? H. This is a rectangular pulse, as your V t. So, I will sketch it this way. This is the rectangular pulse, a voltage of this sort, which is otherwise 0. For t greater than h by 2 it is 0, for t less than minus h by 2 it is 0, here is t equal to 0. This is time axis. So, it is a rectangular pulse voltage, and I have taken such a rectangular pulse voltage whose height is h, 1 by h. Let us take it. Let us take a special rectangular pulse whose height is 1 by h and this is h. Got the point? Suppose this h is equal to 2. If h equal to 2, I will take the height to be half. So, it is like this. For example, if this is plus 1, if this is minus 1, this width of this is 2 and I will take the height half. If this is 1.5 minus 1.5, 3, I will take the height to be 1/3. Acha, what is the area of this rectangle? Half into 2 area of this pulse, area under the pulse, area under the pulse is equal to half into 2 is equal to 1. So, as a general case, if you take this is plus h by 2 minus h by 2, width will be h, and height of this pulse I will try to maintain 1 by h a. Then what will be the area under this curve? So, area under this rectangular pulse will be equal to rectangle. So, width into height. So, h is the width and 1 by h, and that will be 1. Now, you choose any value of h, this will be always true, that is also fine, no problem. But now I am telling you one very interesting thing. What I will be doing is that let to this rectangular pulse, I will try to see h, I will try to make h tends to 0. Then what will be the fate of this rectangular pulse? It will be like this. This rectangular pulse will be, base will be becoming thinner and height will be becoming larger and larger. This is what is going to happen to this, this is time. So, h is reduced, 1 by h is this one. Height of the rectangle will blow up and base will try to collapse. This is what it will be, is not as, and as you say that h tends to 0, but really not equal to 0, that means I will not make h equal to 0, but as small as I can, here, there is here, there is here, like 0 minus and 0 plus. Then the height of this rectangle will go up like anything, it will become a thin strip, and the height h will tend to infinity. Then if h tends to 0, the height of the rectangle will try to go to infinitely large, its height will be as h is becoming smaller and smaller and smaller to whatever extent small 10 to the power minus 68, but the height will then go up. But the speciality of this rectangle is this, if this is h, I will make it 1 by h. The area under this curve, which now becomes almost like a line, will always remain 1. Okay. The height going to infinite, base is collapsing to 0, but the area under the curve remains same. Now, such a function is called an impulse function. As against time, nothing is there for t less than 0, nothing is there for t greater than 0, but at t equal to 0, that is between 0 minus and 0 plus, there appears a value of the function which is infinitely large. Therefore, what should I say about this delta t? So, coming to this next page, I am this part you listen carefully. So, here is your time axis. I am telling that at t equal to 0 there is an impulse. And this impulse is shown by an arrow, because infinite you cannot show the magnitude, it is delta t. So, I will try to describe the function as delta t is equal to 0 if t not equal to 0. T other than 0 value, the functional value of delta t is very well defined. It is delta t 0. T greater than 0, it is also 0. But at t equal to 0, the value of the function is infinitely large. What to write? Going to infinity, going to infinity. I cannot really define what will be the height of the rectangle as h tends to 0, as I told you. But about this thing I am certain, delta t equal to 0 elsewhere for t less than 0. But I can say one thing about delta t, another thing I can say, that is delta t dt between t equal to 0 minus and 0 plus, this is equal to 1, because area under the curve is 1. So, I am collapsing h, height is increasing 1 by h, but no matter for any chosen value of h, the area under the curve is 1. Therefore, this impulse, however high it becomes, so long h you are not putting equal to 0, but collapsing it as close as 0, 0 minus to 0 plus, the area under the curve has to be 1. So, about the delta t function I can say its amplitude at t equal to 0 I cannot define, cannot be defined, cannot be defined, infinitely large. Value of delta t for t other than 0 defined, it is 0, always 0. And then I say, okay, value of delta t is not defined, it is infinitely large at t equal to 0, but this integral is true. The area under this thin rectangle, as thin as you can think of, is always 1. So, such a function is called an impulse function. For example, our any reasonable function of time will be like this, t, it is defined at t equal to this much, what is the value? At t equal to 0, this is the value of the function, any function x t. At t equal to minus 5, it is this much. That is how we are used to deal with function. But here is a function which looks like very simple, because its functional value at any value of t here, 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 all are 0 flat, all are 0 flat. Only at one point it makes its presence felt, that is at t equal to 0, such that delta t tends to infinity, and this integral is true around this origin 0 minus to 0 plus, area is finite, and such a function is called an impulse function. Can we have an impulse function in the laboratory, really you cannot generate an impulse function, ideal impulse function in the laboratory. No, it is not possible. Then question comes, why then study this impulse function? We will see very interesting features about the impulse function and why it is necessary to find out the impulse response of any given circuit. People still on pen and paper I can of course find out. For example, in this circuit, as I told you, if you have a circuit and if V t is equal to delta t, what will be the nature of the current? Can I find it? Okay, in the laboratory you cannot do it, because impulse function is ideal impulse function you cannot find. But on pen and paper, no one prevents you. Study, and what about the impulse function? If such a function which is like this is applied to the circuit, what will be the nature of the current? Will the current will become impulse or what else? Those things we will discuss. Very interesting topics it is. Please, this is somewhat newer, because earlier whatever I have told you was we were really developing the common ground, basic grounds, based on which we can now talk with advanced topics like this. So, impulse function, an impulse voltage if applied to a given circuit, what will be the response, how to find out the currents, this is the topic of discussion. So, for that I must know what an impulse function is, and about this you should not have any doubt what it is. Looking at is, impulse function is one of the simplest function, it does not exist anywhere, here for t less than 0, here for t greater than 0. Only there is some impulse function is present at a single point, it looks like close to a single point, 0 minus to 0 plus. With what property? What will be the functional value? No, I cannot say, it is infinitely large. What about the functional value of this function? 0 everywhere, t greater than 0 plus 0, t less than 0 minus 0. But about these things, this is the useful information. The area under the impulse function will be equal to, unit impulse function will be equal to 1. We will further study this in my next lecture. Thank you.